catalysis of enzyme catalysis is normally low temperature, not like the gas phase catalysis, where gas phase catalysis is normally done at high temperature, like 200, 300, and so on, degrees Celsius. But for enzyme catalysis, normally the temperature is around like 27 or lower than that. Right? This is the temperature of the body, of the human body, because enzyme to catalyze reaction that occur in living organism, like the reaction occur in our body. So that's why the reaction that is catalyzed by enzyme should occur at temperature not more than 27 degrees Celsius. Right? Okay, so enzyme frequently exhibit catalysis at very specific way, as we have already discussed last week. I don't want to continue on that. By the way, if you have not realized that I have already also uploaded the lecture notes. Of course, for the catalyzed reaction 1 and 2, and the other one is for the adsorption, because I think we're going to finish the enzyme reaction today, and then we're going to continue also with the adsorption, probably a little bit on the adsorption at the end of our lecture. Kinetics of enzyme reaction. All right, so we have seen the kinetic of enzyme reaction is not far different from the kinetic that we have seen earlier for the acid-base reaction. Okay, so it involves two steps, as you can see. In fact, three steps, because the first step, an equilibrium or reversible process between the enzyme and also the substrate, and it forms ES, which is the complex, and ES then further react to produce a product, and also the enzyme is released, and then the enzyme can go the further reaction with the other substrate, right? So then we can use what we call as the steady state approach, steady state approach, right, to get the rate for the enzyme reaction. Okay, so for steady state approach, please look for the intermediate. So in steady state approach, as we can see, the assumption there is that the generation of the intermediate is constant, meaning that the rate of reaction or the rate of generation of the intermediate is constant, and it is almost close to zero, right? So when the DES dt, then it is, we can consider as zero. Now, what happens is that, as I've shown you probably earlier, so if you take this as the concentration of the intermediate, for example, and this is the time. So if you see the enzyme, the intermediate is generated initially, and then it maintained throughout the duration of the reaction at very low level, and at constant concentration, meaning that the concentration of the intermediate doesn't change with the time, and so does the ds dt or di dt. Di dt then is zero because it is level, right? So not like the if you see the reactant, the reactant of course will drop this time, right? While the product will increase with time. So I think this is the normal uh, graph that we probably have already seen earlier when we discussed about the kinetic. It's getting hot. Huh? Turn on the. Okay, so for that matter, then the DES dt, as we have seen earlier, is equal to K1E times S. So you have got to look for the reaction that involve enzyme, the first forward reaction which involve enzyme, ES, right? So the reactant is ES, so ES in the equation there, right? And then the backward reaction, right? The backward reaction, right? The backward reaction from ES to E plus S, with K minus 1 as the rate constant, right? So another one, minus, why minus? Because the intermediate concentration is decreasing because ES is consumed. ES is consumed, right? The consumption of ES. So that why it is negative, right? And then another one is negative K to ES because of the third reaction or the reaction after that, where we have ES to form the product, right? So K2 times ES also negative. Why it is negative? Because ES is consumed also here, right? So and then we can do some manipulation of the equation. Then you can get this equation. K1 ES is equal to K minus 1 ES plus K2 ES. And we know that ET, so ET is total concentration. Sorry, total enzyme concentration, right? So where do we get the total concentration of enzyme? Well, during the reaction, what happens to enzyme is that either it is combined with the substrate or it is free in the reaction mixture, right? So that's why the concentration of enzyme, the total concentration of enzyme should be the concentration of enzyme at time t which is not combined with the substrate and the enzyme which combine with the substrate, right? So that should be the total concentration. So what is the total concentration? Is the concentration that you put in during the reaction. When you start the reaction, you know the concentration of enzyme that you use. So that is the total concentration, right? What is the concentration at time t? This is the concentration of enzyme at time t, right? So the concentration of enzyme which is not combined with any substrate. Of course, there is also enzyme which combined with substrate. So that these two will become the total concentration of enzyme. Okay. Okay, so then the concentration of enzyme at any time in the reaction mixture will be the total concentration minus the concentration of enzyme which combine with ES or the concentration of the intermediate in that case. Right. So still people are coming. I wonder why they are too late. Okay, then all right. So enzyme attached with the substrate, or we call this as intermediate just now. But enzyme substrate species in the reaction mixture. All right. So and then you can rewrite the equation. You can rewrite the equation to replace. Right. Okay. Let us see this one. This is we have K1 ES. So you're replacing the E, which ET and ES. And also, right. So the others are ES. So okay, we are left with ES, and then we further do the derivation of the equation by okay. So then so this one is okay. I think you have no problem of that. It's a very simple mathematics. And then concentration of ES from this equation, from this one to this, okay. So the concentration then is of ES, we can get as K1, concentration of ES, I think better write properly, is equal to this is K1 E T, right, times S ES. All right, so what you get from here is right. So okay. So you want ES. So you go there, you get K1 E T S minus K. So if you put the ES on the other side, equal to K1 ES S plus K minus 1 ES plus K2 ES. Okay, so you can do that. Right, let us do it properly. Let's small eraser. Get big eraser. Okay, so what you have here is equal to ES K1 plus K minus 1. So this is another S here. Sorry. Oh, K1 with S, huh? This one should be with S, huh? K minus 1 plus K2. Right? So meaning that what you will have is that the concentration of ES should be K1 E times S over K minus 1 as shown in the equation. K K2 plus K1 S. Okay, so don't confuse with the equation, right? Okay, just to write it properly for you for this one. It should be K. I think the memory is not good. K1S plus. Okay, so anyway, you can do your own to get this equation, which is this one actually. Which is this one. The rate of product formation of the product, rate of formation of product can be written from the second equation, which is this equation. Okay, this equation. So rate of formation of product. So you can just write rate, or people like rate, or certain book like to write V, like something like that, for velocity. But anyway, we only use rate, since I wonder why. Oh, I'm about to finish the battery. Okay, then rate is equal to K2 times ES. So that's the rate for formation of product. So that's why you have rate is equal to K2 times ES there. So then replace that with ES as you get from here. So this is the equation. So again, rate is equal to then K1, K2, where K2 come from is from here. ET. Why we are interested in use ET rather than just E, because E is the concentration at time T, but ET is the concentration that you start when you start the reaction. So meaning that it is you know what is the concentration of ET then. You know the total concentration of enzyme that you use. Start from the beginning. K1, K2 plus K2S. Okay, so and then divide the numerator by K1. So you get this, numerator and denominator. So divide both by K1. So if you divide both by K1, so what you will get is K2 ES over K1, K2 divided by K1. K1, K2 divided by K1. This one divided by K1 will become just by K. Something's not right there. K. This is K1, not K2. So this is K. This is K1. Mistake there, right? So then you have S. Okay. So then, as you can see from here, you have this part, right, which is constant. So this is then is actually K. This is K minus, huh? Km, right? This is Km. So this is called as the Michaelis-Menten equation, huh? And Km is the constant for Michaelis-Menten constant. Huh? Michaelis-Menten equation. So what is Michaelis-Menten equation? So is R equal to K 2 E S over Km Km plus S. So this is Michaelis-Menten equation. Okay, Michaelis-Menten equation where Km is the Michaelis-Menten constant, right? Big Km, right? So if the concentration of substrate is high, you can see this thing is following me, right? Because of the memory of the computer is low, not that large. So that's why it is following. Okay, so if the concentration of the substrate is high, then it is very large compared to Km. So then what you can do is that, so Km plus S is just S. Huh? So meaning that the reaction will become just R equal to K2 ET. Huh? So this is ET. Yeah? No, okay, this is ET. Right? So the reaction just become K2 ET. And this is actually the maximum rate that can be achieved by the reaction. The maximum rate that can be achieved by the reaction. Looks like I cannot write too much on this one. If I write too much, then going to be something like this. Okay, so just using my pointer now, right? So that is maximum. Then you can have this as the maximum rate, RK2ET. So what does it mean here? If you know the concentration, if you know the concentration of the enzyme that you use, you can already predict what will be the maximum rate of the reaction. Okay? Or if you can determine the maximum rate of the reaction, then you should be able to determine the value of K2, which is the second reaction to form the product. So and then you can rewrite the equation, the Michaelis-Menten equation, by writing in this form, where you have replaced K2ET with R max. So R is equal to R max times S, Km also. Need to write it properly, because if you write in this way, people might get confused, right? So and then so you have to write this way, equal to R max times S over Km plus S. So this is okay, but this one, if you write this way, you will get confused. What's the formula of the equation? And when the concentration of S is equal to Km, the concentration of S equal to Km, so if S equal to Km, so then the reaction will just, so meaning that you got two S, you got two S, Km equal to, so this is also S, right? So then your equation will become just R max over 2. So at concentration where the concentration of substrate equal to the Michaelis-Menten constant, the rate of the reaction is only half of the maximum rate. All right, so that is interesting. So, okay, let's go to this one. So this is the, very sorry about that, because that thing is following me because because of the memory of the computer. Okay, put it there. So if you plot V, what is V? V is actually rate. So don't confuse this with the volume. This is rate. So if you plot rate versus the concentration of substrate, rate versus concentration of substrate. Okay, so what you get is a curve like this one, where at high concentration of substrate, so the rate become maximum. This is maximum rate. Okay, and at concentration of substrate equal to the rate constant, or for the Michaelis-Menten constant, so you'll find that the rate is half of the maximum rate. Okay, so rate here is half of the maximum rate. So if properly right, okay, so this is half of the maximum rate. Okay, and the other thing is that reaction follow first order rate law with respect to the substrate or the substance that you use for the reaction, or the reactant in this case, at the beginning of the reaction. Sorry, zero order, not first order. Reaction follows zero order rate law with respect to S when Km is larger than, sorry, this is when Km is larger than, S is larger than Km. When S is larger than Km is at the beginning here. At the beginning here. Okay? At the beginning there. So you can see if you replot the graph of rate versus the concentration of the substrate, what you get is a straight line. So that is zero When Km is far larger than the concentration of S, so you can see it start curving, then that is where R, we can write R is equal to K2 ET times S over Km. So the reaction is then following first order. The reaction is following first order with respect to substrate. So you can see R is equal to K2 ET S over Km. So at concentration, Km is far larger than S. Right. So meaning that you have the combination of zero and first order reaction depend on what stage of the reaction. All right, I don't feel comfortable of using this because of this thing keep disturbing me in the process. So I will want to just exit from notes and try to get the PowerPoint later. It's better to use PowerPoint, it's like. Stop sharing first. So just quick notes for a while. And open the PowerPoint. Section to go through. Transcription. Are you all okay? You are still with me?
Yes.
All right. Okay, thank you. All right. So let's move on then to this one. I mean, I've changed to this. I should share. Let me share it. And then now, window. Color red, okay. For this one, unfortunately, you cannot see my where I put my pen, right? So anyway, okay. So we have seen this. So at concentration larger than Km, reaction follow first order. I've got to check this one. because this is where Km S is equal to Km, right? So this is the concentration lower than Km. So and then you have got concentration far larger than S, where you can do a bit of manipulation to the equation that you have seen just now, and you get this equation. So where R is equal to K2 ETS over Km. So what you can see there is that because K2 and ET are constant and Km is also constant, so it is basically a constant times the S, right? So meaning that so since S is to the power of 1, then the reaction is actually first order. So okay, then important market constants. Okay, the constant. What is the important of the constant is the fundamental characterization of enzymes. It gives the concentration of fundamental characterization of enzyme, right? So meaning that for a reaction, you have a characteristic value of Km for the reaction. So that will define the reaction. So if you have a certain reaction, you know what's the value of Km. And it gives the concentration substrates necessary to bind to half of the available sites of the enzyme. So if you know the value of Km, then you should be able to get what is the concentration of the substrate that you should use to combine with half of the concentration of the enzyme, as you can see from the previous equation or the graph, where you have R max equal to K2 ET and so on. And when the concentration of substrate equal to Km, then you can see that the rate is half. R max over 2. So Km is equal to the concentration of substrate when the reaction is half of its maximum value. So it is an index of relative binding affinity, another one, okay. So it shows how strong is the combination between the substrate and also the enzyme in this enzymatic reaction. And the values are expressed in millimolar. So Km has the concentration unit. Concentration unit. Okay, so it is in millimolar. And the value can be determined from the plot of, this is in the plot that you're going to see later, right? So this is a plot of 1R over 1S. 1R, not over 1S, versus 1S. And this is, in this one, it is written as CS, where CS actually, CS here is actually the concentration of the substrate, right? So what you can get, so if you go back to the equation, so what, that's why it is difficult here. R max S over Km plus S. R max Km plus S. So this is your rate. This is your rate. Okay, so then if you take 1 over R and so on, so what you get is you take 1 over R. 1 over R will be Km plus S R max S, right? So, and then if you further do it, Km over R max S plus 1 over R max. So this is your 1 over R. So this is the equation. So this is actually what we call as line Weaver-Berg equation. So line Weaver-Berg equation. So if you plot that 1 over R versus 1 over S, 1 over R versus 1 over S here, right? So this will be your, this is your tangent. This is your tangent, right? Or your slope of the graph. Tangent or slope of the graph. And this is your what call it, intercept of the graph. Okay, so that's why you can see the intercept there is 1 over 1 over R max, the intercept, right? And the slope is Km over R max there. And also you have another one. This is when 1 over Km. When 1 over Km occur, or 1 over Cs, 1 over concentration of S is equal to minus 1 over Km. And this occur at 1 over R equals 0. Okay, so when 1 over R equals 0, you can see 1 over R equals 0 here, right? So you can see the line is here, and that is equal to 1 over Km. If this is 0, then you can work out how the 1 over, how you get this relation of 1 over Ks and equal to 1 minus 1 over Km. So meaning that what you can do is you can also determine the value of 1 over Km at this position, or you can also determine the value of Km at this position. You got two choice, and you can also determine the value of Km here, right? And here. So normally what we'll do is just to determine the value of Km by using these two values that we get here, these two values. This is the slope and also the slope and also the, so you got slope, just write back, slope is Km over R max, and your intercept is equal to 1 over R max. So if you, for example, you determine the intercept first, you get the value of R max, and then after that you determine the value of the slope, you then can determine the Km value from there. Or you can also determine the value, Km value also is just the slope over the intercept. So slope over the intercept is really the Km value. So if you can shortcut that if you want just to determine the value of km. But it's then okay also if you want to, you can also determine the value of Rmax first, and then the value of the km. So it is more often used as it shows the dependent of variable of S and dependent variable V. V is the rate. So meaning that this is actually to tell you it is actually the plot of rate versus concentration. Right? So meaning that the rate will depend on the concentration. So the rate will change with the concentration. That's all. Okay. 1 over rate approaches infinity as S decreases. Right. So as you can see from the graph, 1 over 8. This is 1 over 8. 1 over 8. If you move to backward, to the concentration, to low concentration, what you'll find is that the 1 over 8 approaches infinity. Approaches the value of infinity as the concentration of the substrate approaching 0. Okay, and this gives undue weight, and this is going to be inaccurate measurement. So this is an inaccurate measurement, so it is not good then to use the line Weber plot at very low concentration. Okay, so not going to be accurate. So and then the second one, give the insufficient Nuros Chamira is left giving the meeting. Not sure why. Give insufficient weight to more accurate measurement at high concentration. And then the other one is that at high concentration, is as such that the value is very accurate at high concentration. So meaning that it's this shows that the line Weber plot is not so good at extreme concentration. Whether it's low concentration or high concentration. So meaning that if it is like intermediate concentration, then it is good to use line Weber plot. Right? So what is the alternative? We can use this as the alternative. So you know earlier that rate, what is the equation? Forgot again. R max S Km over S. R max S, back to the equation, Km, which is the Michaelis-Menten. So this is back to the original equation. You don't have to remember all this equation. You can always go back to the original Michaelis-Menten equation, and then you can then get this equation, right? So this is called as Eddie-Hofsey. How do they get this equation? Okay, let us see. Right, is equal to some manipulation of the equation. You can see that R is R here, right? And R here, right? So then you can see that the plot is between this is R versus R over S. Okay, so from here you need to how you can get this equation. So what you do is just plotting R, which is the rate, versus R over the substrate, and then you get value there. And from here you can see that low concentration, which is here. This is low concentration. Where the value of V over S is high, then you can actually get the value of P over K. Now this is where R equal to 0. R equal to 0. And then one is you can get the value of maximum rate. This is R max. R max. You can get the value of R max. Okay, you can get the value of R max at V R over S. At R over S equal 0. At R over S equal 0, then the whole thing will be 0. So R will be equal to R max. Okay, so this is another one that you can use to evaluate the value of R max and also the value of Km. Km is still you can get it from the slope of the graph. Alright. Okay, 919. So this is an activity to do. Glutamate 3 hydrogenase enzyme catalyze the breakdown of amino acid and glutamic acid according to the reaction scheme proposed by Michael Smelton. The steps involve reversible formation of enzyme substrate GLDGA, complex followed by conversion of complex to the product. Okay, this is the normal enzyme reaction that we have just seen. So only thing here is that you have the GA, the enzyme which is GLD. Oh, sorry. Because it reached the end of the slide. Okay, so you have GLD as the enzyme here and GA as the substrate. So you have got GLD enzyme plus GA as the substrate, of course. So and then what you have is the normal reaction K1, K minus 1. So you have GLD, GA, and then after that GLD, GA will form the product. Like SP, and then there you get back the enzymes, which is GLD. Okay. So what you have to do is to derive the Michaelis-Menten equation from the breakdown of glutamic acid. I think that's not difficult for you. And the rate of breakdown of glutamic acid and constant concentration of glutamate dehydrogenase as follows. You are given the concentration. You are given the concentration, and also the V here is of course rate. Okay, as given there to you to evaluate the value of the Michaelis constant Km and the maximum rate of high substrate concentration. So you have got to determine the value of Km and the maximum rate. So two things that got to do there. Got to determine the value of Km and also R max. So how are you going to do that? So as you can see from here, you are only given two set of data, right? Two set of data here. So normally for two set of data, we don't do graph. We don't do graph. You don't have to plot graph. So what you got to do is you can also use what you call as the you can write into form of equation and just solve for KMRX. Right? So you write two equation. You write two equation and solve for KM and R. So that is what you have got. Right? Okay, so you can do that as the activity for you. And we can now move on to the next one. All right, so I want to start the absorption. So let me just take the absorption out. All right, so now we are moving on to the next topic, which is absorption. So we have finished with the catalyst reaction. So in catalyst reaction, we have seen two main things. One is on acid base reaction or acid base catalysis, and the other one on the enzyme catalysis. Both are homogeneous reaction. Both are homogeneous reaction. And so we have gone through a number of equations that is relevant for both acid-base reaction and also the enzyme catalysis, right? And then we end with the Maclaurin-Menten equation. So I have already given you an activity to do for that. So we see about that, right? Okay, so let's start with the absorption. Okay, so absorption normally occur between two involve two phases. So you know that the absorption. So if right, so let's go back to this one. And so make sure I have not shared yet, right? Sure. Share. Go back to share. Is everyone okay?
Okay,
All right, good. Okay, so let's move on to this one, to the next topic, which is on in terms of the area. So meaning that the surface area of the internal surface is the internal surface is far larger than the surface area of the internal surface due to what we call as pores. These are pores. Due to pores. So these are all pores. right? So they can come in different size, in small size, in big size, and so on. So we'll see that later. So what are the learning outcome of this? To differentiate between absorption and absorption, AB and AD. So you should be able to differentiate what is what is absorption. To differentiate between chemist option, what is chemist option, what is physics option. To describe absorption isotope, you got the IUPAC absorption isotope, Langmuir absorption isotope, Brunner, Hammond, and Taylor absorption isotope. And to relate absorption isotope to the surface area. Okay, so these are the terms that you should be familiar with for this topic. What is adsorbent? What is adsorbate? What is absorption? What is absorption? And also desorption. There's another thing that I have not yet tell you. Desorption. So as you can see from the previous slide that I've shown you, all right. So the absorption process occurs when you have the say A as the adsorbent and B as the substrate. So the reaction will occur and you get the absorption of A to B. So meaning that the forward reaction is absorption, right? Absorption, and the backward reaction is desorption. So what it means that the A and B, although they have already formed, depending on the kind of bond that form between them, they can also split back into A and B. They can split back into A and B through the desorption process. If there's very strong bond between A and B, or the affinity of A to B is very, very high, then it is very unlikely that the A and B will split back into A and B. But if it is the interaction is weak, then it is very highly likely that A and B, AB will dissolve, or the desorption process will occur or form back AB. Okay, so meaning that the absorption process is actually also can be regarded as the equilibrium process or reversible process, depending on the affinity of A to B or the adsorbate to adsorbent. Right. Okay, then you have absorption process, desorption process, associative absorption. What is dissociative absorption? Associative absorption, dissociative absorption. We're going to see that later. All right. So then this you can find yourself what is how do you define absorption and absorption? Please find out what is adsorbent and what is adsorbate. As I mentioned to you, please find out how you define that, how you explain that in words. Differentiate between absorption. When you define it, doesn't matter how. There's not only one way of defining. You can this is define is just to know your understanding. What is absorption? What is absorption? For example, what is adsorbent and what is adsorbate? It is not like having one type of phrase only for defining. You can have a number of type of phrase. Different type of phrase. You can trace to your understanding. All right. Okay, and make sure that other people will understand also. So if you answer the question in exam, so you have got to make sure that what you have written is understood by the examiner. Differentiate between adsorption and absorption, and differentiate between chemisorption and resorption. That you can do yourself. Okay, probably you can see this one. This is the resorption and chemisorption. Okay, resorption, chemisorption, long range bonding, short range bonding. Okay, resorption is physical adsorption. Chemisorption is chemical adsorption, right? So when it involves chemisorption, meaning that it involves strong bond between the adsorbate and also the adsorbent. So that's why you can see that this short range bonding, right? And it sometimes form chemical bond between the adsorbent and adsorbate. While for the resorption, it is only weak, long range bonding, and normally it is in van-der-Waals form. Van-der-Waals interactions. If it's stronger than van-der-Waals, then it could be like hydrogen bond, for example. Hydrogen bond. Okay, that is also another one. The type of interaction that can occur between the substrate and also the adsorbent. Not surface specific and space specific. So it depends on what type of adsorption. Resorption is not space specific. So meaning that you can see the van-der-Waals interaction, it could occur between different type of surface. While for the chemical adsorption, so it only occur between certain surface. So to form the bond, the chemical bond, it is not just any surface. So if the adsorbent with a certain functional group come to the surface with also a certain functional group, then the reaction could occur and form bonding, right? Form bonding, and this bond is very strong, and that is chemical bonding, and it can occur only with certain surface. So in terms of the energy of the reaction, you can see that the energy of reaction for the resorption is quite low, between 5 to 50 kJ per mole, while for the chemisorption it is quite high, between 50 to 500. Right? So the resorption involves non-activated with equilibrium achieved relatively quickly, and then for chemisorption can be activated, in which case equilibrium can be slow. So one is very quick in terms of achieving the equilibrium. The other one is quite slow in achieving equilibrium. Because this is a reaction, this is actually a chemical reaction when you consider the chemisorption. No space reaction. You can see other thing is that increasing temperature always reduces the surface coverage, right? That is the characteristic of the resorption. While for the chemisorption, temperature can favor adsorption. An increasing temperature can favor adsorption. All right, so you can get more adsorption to occur at high temperature. Well, for the resorption, as you can see, increasing temperature also reduces the surface coverage, meaning that the high temperature favor resorption for resorption rather than adsorption. So that's a big difference between chemisorption and also resorption. No surface reaction. So this is the resorption. It involves no surface reaction, meaning that if you have a molecule get absorbed on the surface, there's nothing happen to the molecule. While for resorption, the molecule is absorbed on the surface, and the molecule have changed to a different form, no longer the same molecule as it started. It can occur in multi-layer for the physics option, and it occur only in monolayer for physics option. Meaning that for chemistry option, only one monolayer is formed. Meaning that only the layer between the adsorbate and also the adsorbent will be in chemical bond. Other layers could be in physics option. While for the physics option, you can have a number of layers, and each layer is physics swap to another layer. All right, I think we can stop there for now. It is 9:41 now. So what we're going to do now is we have at last we have quiz. So what should answer for the quiz? What you should answer for the quiz, if you go back to the activity that I have just given you just now, you go back to the activity that I just given you just now, and answer the question on getting the value of R